Okay. Hello, everyone. Welcome back to our next session. And thanks for joining in. So today we are going to look into measurements. Right, what did we do until now? We were designing, like we learned the very basics of how to design primers and so on, and then we designed gates, and we actually designed a real Hello World program last time. And so once you have designed it, you will go to the wet lab, right? And you will construct it. And this is actually also what we're going to show you in a later session. But now we assume that we have this actually. And you want to do some measurements of this, right? Like you have your circuit running in the bacteria. So we have here, let's say we have here our E. coli with classically its genome, right? And now we have inserted here, this here is our design, yeah, that we constructed, for example, last time, or that you will do in the homework, for example, the inverter. And we want to gonna test this. We want to see what is the performance of this thing. So how we are going to do this? And there is kind of course, there's tons of measurements. You can measure many things, and you will some measurements are very specific to specific protocols. Yeah, for example, I don't know if you want to know how many or where exactly are my ribosomes sitting and my RNA. This is really not going to be covered in this lecture, all the specific ones, but we are going to cover the very broad ones that you will be using probably every day or very often, and that we think are very have some nice concepts to show. And what are these measurements? Yeah? So the first thing you could measure is actually some population level measurements. Yeah? So you will not have a single E. coli, you will have many E. coli. So probably you will have around 10 to the 8 per milliliter E. coli, yeah? Or something in this range. Let's say if it's not so highly concentrated, it's 6 to 8, something in this range. Yeah? You will have in your sample. And so this is your sample. Right? And now we want to do some measurements with this. Yeah? So this will be so-called bulk measurements. Yeah? Bulk measures. Yeah? So that means like we're measuring the properties of a population. Yeah? Okay. What can you measure from this? So very concretely, what you're very often interested is actually really this number here. Like how many bacteria are in my culture? So why is this interesting? You can think of the following, for example. You can think of the following experiment. Here is our time. Here is our number, or number per ml, so the concentration, right? And we're interested in the so-called growth curve of this cell. Well, in our case, it will be the bacteria E. coli. So let's say, so of course, there's different ways to plot this. Often you will plot this in a log plot, right? So then this will typically have an exponential phase here, and then it will go down to a stationary phase here. Right? So and since it's a log plot, the exponential will look like a linear here. So and this gives you many properties. So you will read off, for example, about this inclination, about the growth rate here, or you will know when does this go to stationary phase, when perhaps does it go even down. You can compare this. You can couple this with fluorescence measurements, and so on and so on. So there's lots of information in this plots. So these are very basic plots, and we will look into one snapshot here. So at the time t prime, what is the actual concentration at this point in time? Yeah? And now if you do this repeatedly, you get your growth curve, for example. Yeah? There is also other kinds of measurements, and today's lecture will be focused on these bulk measurements. We will have a later lecture where you really look into single cells, so single cell measurements. Some principles of what you will learn here can also be applied to single cell measurements, but a very big example of what is normally done with single cell measurements is actually microscopy, right? You will really look at single cells, how they fluorescent, how they look like when they duplicate, and so on. And we will have a particular lecture about microscopy in I do have to look up when, but I think in 2 sessions or 3 sessions. Yeah. Okay, so today, bulk measurements. So let's take a look at the online material. So we will be using a library that is called Raman Spy. Yeah. So then that's actually a quite nice library that comes also along with with links and tutorials to very interesting data sets. And this is why we picked that. We will be using that. So here's just how to install this, of course, like always. Then we have, as usual, and as is good practice, we are now doing logging, right? We introduced this last time. So here's like we set up our loggers just to not always print if something is happening bad, but actually to use logging. Yeah. And then we start with the simpler of the measurements, and this is actually absorbance, right? Because what you will do actually without even noticing that it is a measurement is you will hold your flask, yeah. So here's your flask with your liquid in it. You will hold it, and you will look through it and look if it's kind of turbulent, like turbid. If you see some kind of like how the absorption of the light is through this liquid. Because traditionally, like this liquid will be, for example, if you're using LB, which we will be using in the lab, this will be kind of a yellowish but transparent view, and then it starts to be very turbid, and once you have something like 10 to the 8, 9 E. coli per ml, it will become very you can hardly see through it anymore. Yeah, so you see this by the eye. The thing is, of course, this is not a very precise measurement, but it just gives you a kind of set point whether you are reaching something in the order of 7, 8. So you can detect this quite late with the eye, but it's a kind of a rough measurement. And the question is, can we do this more systematically, and can we do this with equipment, but relying on the same principles and on the principle of absorbance? And the answer is, of course, yes, we can. And this is not something very new. This is done since ages. That people project some rays of light from, let's say, this side against the sample, and they are looking how much is being received on the right side here, and just noting kind of the difference, or the ratio we will see. We think that the ratio is quite nice between this incoming light. It's called as 0, right? Because we can view this as a kind of an x-axis here, and this will be, let's say this has width W, then this will be the outgoing light at position W. And we can, there is some information in this. To see why there is some information, I mean, conceptually it's clear, right? Like the more there's inside, the less light we are supposed to get here. I mean, there is, of course, conditions. Like as long as this thing interacts or disturbs rays of light going through. If you think, for example, you are dissolving sugar in this, unfortunately, you will not see much here. I mean, of course, if you pour in like a kilogram of sugar, then you will see an effect here. But like in the beginning, like you have a large range where you don't see much. But this is not the case for E. coli or something. For E. coli, it's actually a bit subtle why it's not the case. But something, for example, if you pour in sand or milk, you will very soon see that this gets milky or sandy. Like you will very soon notice something here. And what's your intuition? Like, let's say I have a concentration C, and I'm going to a concentration of 2C. So I'm doubling the concentration. What's roughly going to happen here? And actually, it's not so clear if this W is not negligibly small. We will see. It's very clear what happens if we have a very small slice. That's not difficult, but it's not so clear in a larger space. And this is roughly, so how long is this difficult? Well, this will be something in the order of 1 centimeter or something. I mean, it's a kind of a cuvette that you put in a device. There exist, of course, much smaller ones, but the typical one will be like something in the order of 1 centimeter. Okay. Like whenever you have questions, feel free to interrupt me, of course. But otherwise, we will try to understand some properties of this IW here, what's happening with respect to the concentration here. Yeah? And for that purpose, we can look at this picture, and I'm going to quickly redraw this here to show you some properties on it. So I'm going to remove that here and keep these things here. All right. So the first thing I'm going to do, I will focus on a single slice here. Let's consider this slice here, and let's say this is actually the slice at position X. Yeah? And we will assume that it has a little depth, yeah? A tiny one. So we will, I mean, here it's not at all tiny, but conceptually it's very tiny. Yeah? But you should actually see that, what I'm doing. So this is X plus some delta X that is supposed to be, I mean, if I write delta X, we will actually, you will already know that we are letting go it to 0 afterwards. Yeah? So what's happening? And let's look at the properties from this side and this side. Yeah? So from this side, we are going to have Ix, and from this outside, we are receiving X plus delta X. Good? Just by definition of the I's. Yeah? So I is the intensity. Yeah? We are assuming a few things. So first, we're assuming that this is kind of, I mean, all of you know, like, we have to be very careful when we have some models of light, right? Is this a wave or a particle or so on? But we will use a very simple model of light here, yeah? And this will be completely enough for us at the moment. So we will have just rays of light. Yeah? Yeah? So we will assume there is parallel rays of light. So we assume light that is parallel here. Yeah? There is no diffusion thing going on here. And this will be important afterwards. Huh? And so what we are receiving is kind of, yeah, let's assume for the moment we are receiving here really parallel rays of light. So now we have some particles in there. This can be, for the moment, let's think of particles that are really blocking light. So we have, let's say here we have one particle. Here is another particle. And here's another particle. Yeah? And what is happening is actually, if a ray of light is hitting this particle, it's being blocked. It's got absorbed. If it's not hit, it gets through. Yeah? So if we send in n rays here, how many rays do we get here? I mean, this is it's kind of a game, yeah? Because of course I could be nasty. I could align all my particles in this way, right? And then there is only one ray absorbed, let's say, or two, however thick this was. Yeah? But of course, this is very, very unlikely to occur. Yeah? So in generality, we can assume that they are well distributed. So we're going to have something like this. Yeah? But of course, for not too high concentrations, because if the concentration gets very high, let's say I just pour in a bag of sand, I mean, then the particles really will be just behind each other. Yeah? So our model will be not holding here anymore. But for not too high concentrations, we will actually have some particles not hiding other particles roughly. Yeah? And if they do, very, very small ones and so on. So we can just neglect them. Yeah? And this is what you see here also on the screen. Like here, this black particles are blocking light. Yeah? So what, can you tell me, I increase my concentration with a factor 2. That means suddenly I have double the particles. How many light rays, or by how much will I reduce the light rays that go through? Yeah, exactly. So it's very good. You see, it's very simple with this delta X. If we have a small slice, it's just proportional to the, it's completely simply proportional to the concentration. Yeah? But of course, you see the limits, right? If I keep increasing, then of course, at some point we lose this range where we assume that they are not behind each other, shadowing each other. Yeah? But here it's still quite fine. Yeah? So if we if we do that, if we completely assume that this is the case and this is roughly the case, right? Then we have actually this formula here. So we have that just the received light at the outside here, right, is what we got at the inside here, minus, and this is a factor we don't care for at the moment. It's just some proportionality factor. This we put it in for a reason. We put it in to get actually from the concentrations to the numbers, right? But it will not play a too big role. And then yeah, we are multiplying this so proportionally with the concentration to this incoming light. Yeah? So this is kind of what we are removing from the light. Yeah? This is why do we have an I here and not just a minus C? Well, this is just essentially because I don't know the kind of the density of the rays here, right? I would have to remove more rays if they are very dense, and less rays if they are incoming very sparsely. Yeah? So this is kind of accounting for this. Okay, and this intuitively this thing here, yeah, there is some facts in here. Yeah? So for example, one fact that is in here is actually how much is one particle blocking light. Yeah? What's kind of the area it takes away where it interacts with light, blocking it. Yeah. So yeah. And of course, for an intransparent ball, you can think this is just its yeah, it's the sphere that you get by cutting the ball normally orthogonally to the rays, right? But you can think of more complicated structures where it's not so clear. And in particular, and this is quite interesting, I think. In particular, you can think of something like an E. coli. That will actually not much block light, right? Because an E. coli, I mean, if you look at it under the microscope, it's something that is actually quite difficult to find, yeah? Because it's not something a priori, it's not something green or pink as I showed it here, yeah? This is just for demonstration. It's something very transparent, and you have to use some tricks to see it. Yeah? So what is it going to do to our light rate? It's actually not much blocking them, but what it is doing, it is actually refracting them in some other direction. Yeah? So this is what's going to happen. So if you shine a light through hitting here, this light beam gets refracted, let's say, in this direction, and this one gets in this direction, this one in this direction. Yeah? Of course, in reality, this refraction will not be random. Yeah? But for us, it's a good enough model to be random. Yeah? Because the surface is not, let's say, if you would have a very nice surface, you could say, okay, it's just reflecting. Yeah? But this is not the case. It has, of course, some physical properties where you could, in principle, calculate the refraction, but since they're moving, and it's definitely a good enough model to just assume if I hit it with a light beam, this is going in a uniformly random direction. Yeah? Simple model, but a good enough model. Yeah? So, and actually, what is the outcome? The outcome is about the same as being blocked. Yeah? Because, and this was why it was so important to have parallel thing here. Because now this light will go in this direction, yeah? And it will not hit my sensor here on this. So it's kind of out of the game. Yeah? Of course, you have a very little probability. Yeah? I mean, to exactly hit this, you have a 0 probability, but the event exists. Yeah? But let's say to hit in this small range here, you will have a small probability. Yeah? But again, we can say this probability will be very small. Let's neglect this. Yeah? For the moment, you're a little bit underestimating the concentration, but this is fine. But it also shows another principle. It shows you should be careful when you collect here the light. For example, if my sensor to collect light is very big, it goes from the bottom of the floor to the top of the wall, then actually I'm collecting this one and this one. So I don't want to do that. I have to be a bit careful. in trying to collect only this ways. Yeah? And what you often do is like you make a small hole here on this side, yeah, that has exactly this shape, and where you're really only collecting the things. Yeah. For example, if I have a hole of this size, yeah, and I move it quite far away, I mean, it should not be too far away to diminish the light, but let's say I move it here, then you have to really be almost parallel to hit into this hole, right? So this will not hit, this will not hit, this will not hit, and so on. Okay. So this is two principles, yeah, by which we obtain this very simple approximate equation here, right? How light is diminished. And now we're going to use it. We have the physical properties for this slice here. Yeah? And now we go with delta x, we can go to 0. Yeah? And we can just put one after the other. Yeah? And this is not too difficult because it's almost, I mean, you recognize, I mean, if you put this ix to this side, yeah, you have ix plus delta x minus ix, and then I divide by delta x. That's actually very nice, the differential operator of I with respect to x. So we were very lucky. And this is what is done here. You can look that up. There's some delay. This is what you see here. Okay, you don't see the fraction here, but in general, this is not it's a bit pixelated, but okay, yeah, you get the principles. And so this is the differential equations we get. And of course, I mean, you will immediately know the solution, right? This is like perhaps the first differential equation you learn in school. This is actually what's the solution. So we have something that's starting off with I0, if x is 0, yeah, which by the border condition, this has to be the case. And then is exponentially decreasing, and the exponent is minus gamma cx. Yeah, that makes total sense. So the further I go into the medium, the more my exponential diminishing is happening, the higher the concentration and the bigger this inference coefficient gamma is. So we get a very nice rule. And if you plot that, that would look something like this, right? We have here, let's say here's our x. Here I'm going in with a certain light. Yeah? And then from here, I'm exponentially going down with the amount of light. And this is, let's say, the light that comes out. If I repack that here. Yeah? Okay. Everything clear until here? Yeah? Okay. There is a little problem with, so first of all, to give credits, who did this? This is kind of a simplified proof. And I will give you in a second the explanation why this is a bit simplified, but this is a simplified proof of a very nice rule. This is the Beer-Lambert law, yeah, that you can look up, and that is the principle of actually using such light intensities to measure concentrations, and we will make that very clear how to get that C. I mean, you can already get the point, right? How to get the C. In principle, you measure this, you log this, and then you get out the C, and this is what we will be doing. But just before we will do this, there is a tiny small, perhaps too much simplification in this formula, yeah, and that is actually, if we set C equal to 0, we will see that. So I told you, I mean, what happens if we set C equal to 0? Like, and why is this useful? So if we consider the case C equal to 0, that is the case actually where your cuvette is completely filled with, for example, in our case, LB medium. Yeah? But I told you that it's kind of a yellowish. I mean, I can see the difference between having a cuvette with LB here and not having it here, like looking out of the window clearly. Yeah? So there is clearly something happening to the light. Yeah? And in fact, of course, the LB medium is not totally transparent. It is diminishing the light. But if we set it to 0, so we put 0 E. coli inside, and now we are going to use our formula here, right? So what is our formula? It's let's call this W. It's the width W of our cuvette. If I set this to 0, that goes away because it's 1, yeah. And it tells me exactly the same output light as input light, yeah. That's totally true for something totally transparent, but it's definitely not true for my LB. Yeah? So to be precise, I cannot use this formula for LB. Yeah? And this is also important because this is something people do, right? We will see this. This is called blanking, yeah, like measuring just the pure medium, yeah, as a reference, and that would not make sense, yeah, because why do a blank if I can just tell you it doesn't do anything, yeah? So of course it's not the case, yeah. So this formula is already a bit too simple, yeah. But fortunately, if you keep in mind the proof, you will have a very easy time to derive a more complex formula that takes into account this. And the only thing we have to do is we have to reconsider our delta x thing, yeah? Where we had, let's say, here were our E. coli, right? And they were blocking some light. Yeah? So they were removing light of the amount minus delta x gamma and the concentration of the E. coli C times, of course, the incoming light. Right? So it was proportional. That was the proportion they were removing. And now it seems that LB is kind of also removing. Yeah. So let's simplify this and say there is some LB species. Of course, this is, as you see, this is a simplification. There is no real LB species. LB is a mixture of many things. But we can assume that there is a homogeneous, very fine-grained thing that is also removing light. And so we can just say it's also removing. Like when I hit this, light hits these particles here. They're symbolic particles. They're not like real particles, of course. Or there's real particles inside, but they are not homogeneous. But we assume them to be homogeneous for the moment. Then we have minus delta x because this is the same. Then we will have a gamma prime that is specific to these things. Probably it's much smaller than an equilibrium. C prime, so kind of the concentration of this thing here, and also Ix, right? And then we go back and do the same proof, and all you will notice is actually, that this is only going to do something like this here. What was here? There was a lambda C plus lambda prime C prime W. Yeah, exactly. Totally, yeah. So you will be, because it behaves just the same way. And again, you have to do some little assumptions. You have to say that the sum of this concentration is not too much, or that such particles will not be hiding all behind this and so on. They're like all the standard assumptions that we are in a kind of a mid-range of concentrations. Okay, and now blanking makes sense, because if you blank now, this is going to remove just this here, but it's not going to remove this, right? And now we can actually look what happens if we are measuring, because this is what people do. If we are first measuring LB, right? Then we will get some, so we will put some I0 against it, and we will get some I think I called it blank BLK here. Let's be consistent. Yeah. Yeah. Okay, this is already, but let's call it blank. blank here, get this out. And then we do the same thing with the E. coli. We have I0 here, and we will get some, now this is a W, and this is removed. This is LB and bacteria, right? And we will get some I measurement outside. Huh? And what is actually done is that this property is taken. So what people take is actually minus the, we will use a natural logarithm here for simplicity, but this is just a, you can recompute this for the to the base 10, what is usually reported by such devices, minus I x, or IW in this case, divided by I0. Yeah. So this is a measurement. Yeah. And we know that this is actually equal to gamma C plus gamma prime C prime W. Right? And depending now, if we make a blank measurement, so let's take this measurement first. So if we make this with M for the measurement itself, we will have the minus log the measurement divided by I0, right? So this will be exactly what is written here. And if we do it for the blank, we will have actually minus log I blank I0. And this is actually, we said that what I don't want to choose it consistently with the gamma prime. I think we use this for the E. coli, this one's here. So this will be 0, and we will just have gamma prime C prime W. Okay? And what you see now, if I take my measurement and subtract the blank measurement, I'm subtracting that one. Yeah? So I get this. Right? So what I will get here is actually gamma CW. Yeah. So I will get a measurement, and this is called the optical density measurement, that is proportional to some gamma, which we don't know, that is proportional to some concentration, which is actually what we're interested in, and that is proportional also here to the width of the sample. Yeah? And this is kind of the optical density after blanking will be this. I mean, I'm a little bit chickening here because we took the logarithm to the base e, and normally we report it to the base 10, but this is, you get the principle here, right? Okay, this is written in more detail here. There is perhaps a very small neat trick already written in this formula, and that trick is here. Imagine, so many devices can actually read only up to some, let's say, for example, ODE of 4. Yeah, that is kind of when they max out. Yeah? This depends on your device, of course, but let's say it maxes out at 4 our device. Yeah? So let's assume the real ODE would be something like 6, but we are just display the maximum. Yeah? I cannot measure this. It's above. It's above 4. Yeah? Then you see something with this W, what you could do here, yeah? Because if this, in reality, let's say, would be 6, yeah? But we don't know yet, yeah? So in all cases, it's bigger than 4, yeah? What can you make to reduce this measurement here if you can control W? I mean, we could, for example, make W smaller, right? We could use a W divided by 10. Yeah? So that would be kind of inserting a cuvette that doesn't look like this, but that looks like, I don't know, that looks like this. Huh? that has 10 the width. I mean, it will be perhaps have something like this to be inserted in the same device, but in principle, the liquid can be only in a small slice here. Yeah? So we are dividing this by 10. And actually, I mean, if you do that, your ODE, according to our formula here, will be divided per 10. Yeah? So suddenly, we will get something like, for example, 0.6. Yeah? And then we know, since we have this, if we retransform this to the classical ODE, we will have actually 6. Yeah? So it's a neat way of not having to dilute your liquid. Yeah? Because the other way you could have done is like you take your liquid and just dilute it by a factor of 10. Yeah? But this is error prone and so on and so on. So this is a neat trick. This comes out of the formula directly. Yeah? Mm-hmm. So this brings me to the end of absorbance and optical density measurements. Yeah? That where optical density was these things here. Yeah? So optical density being the slightly more general principle than absorbance. Absorbance was taking away light, for example, by sand particles, and optical density also taking into account this random diffusion of light like E. coli. They don't absorb light, they refract light, but still making such measurement possible with this Beer-Lambert law, essentially, or this the very simple generalization of it to medium. Okay, give me just a minute to take some water. Mm. If you have questions, of course, now is a good time. Otherwise, I'm going to continue with the next chapter. All right, let's continue. And this is actually something that is called Raman spectroscopy. What I didn't tell you until here is like when someone does optical density measurements, yeah, what you very typically use, your incoming light, yeah, will be actually from a certain wavelength. Yeah? For example, it could be from the wavelengths of 600 nanometer light. Yeah? And then from this, we get some optical density, which is typically denoted with the wavelengths at the bottom. Yeah? And why is this the case? Why do we need to annotate something with the wavelengths? Yeah? I mean, for something like, for the simple principle of just blocking light, that would be not very important. Like if a sand particle just blocks light, we don't care about the wavelengths. I mean, of course, if it behaves like a wave, yes, we care about it, but in our simple picture of rays of light, we don't care. But we care very well when we look at refraction. If it's something transparent and it's just diffracting light in different ways, yeah? Because it might diffract light in a very different way at 600 nanometers, for example, than at 700 or 800 nanometers. Yeah? So you will get different optical density measurements depending on the wavelengths. Yeah? And if you do this conceptually for all the wavelengths, you will get something that is called a spectrum. Yeah? You will have here the wavelengths. There, yeah. And you will here have kind of the optical density. Yeah? And this is something. For example, let's say let's make it in. Yeah. Okay, let's say this is at 600 nanometers, yeah, but that at 700 it looks, for example, like this. So you get something that is called a spectrum. Yeah? It is kind of like the absorbance at different wavelengths. Yeah? And you can use now another principle that is not based on absorbance, yeah? But on a little bit more complicated thing. Yeah? And this is actually useful to obtain something that is called a Raman spectrum. Yeah? I will not go here into the physics because not for the reason that it's too complicated. You can actually check that out. There is actually the Wikipedia article is quite nice about this. Yeah? But just because we actually don't care like what is being done. Yeah? But what you can think of is like that the different structures, the different bonds, yeah, in your chemical product or in your biochemical product, will actually absorb yeah, the incoming light in different ways. Yeah. And this is what we will be using. Yeah. But what is perhaps important is that the thing that we will be seeing here, yeah, and this is like kind of the setup. So this is a nice figure from Wikipedia, where actually like a laser with a laser beam is actually being reflected against the beam splitter. This goes down and focuses up against the sample, right? And there is a spectrometer that is very similar to what we did. Just it's using a CCD, so it can do this in parallel, reading all the kind of the absorbances at the different or the resonances at the different wavelengths. But the principle is like that you get a spectrum, and the things that we are going to see are not specific to Raman. Yeah? They are really, you could use any spectrum essentially. Yeah? We are just using it as an example of Raman because this is a technique that is more and more being used in biotech, and this is why we thought it's quite useful to look at this. Okay, I will go over this. This is a bit technical. Why something is, for example, reporting the wave numbers. But this is okay. We don't care about this, but this is using this package, for example, about how a typical Raman spectra would look like. Yeah. So this is such a spectrum. I mean, this is a synthetic spectrum. Yeah. It's not a real spectrum, but this package allows you, for example, to generate some. You can think of it like this. And if you look at it, we see kind of the components. Like you see, there is always these peaks, right? Essentially it's an kind of an additive overlay of these peaks. And a very simple model perhaps, but still a useful model would be to assume roughly a Gauss function for these peaks. Yeah? They look roughly Gaussian. Yeah? So they have a clear mean, like a clear center, and then it looks like a bell curve, right, on both sides. Yeah, and we see also they have different sigmas, kind of, if we speak in the language of Gauss, that there is a higher sigma here than, for example, here. Yeah? So it's kind of a, yeah. So this is, you know that from statistics probably, this is like a simple PDF function of the Gauss distribution, or let's say the Gauss function, right? And we are just coding this here, and we can now use that to do our own synthetic spectrum. I mean, not as advanced as the other one, as you see here. We just used two very simple peaks and we added them up, but that's our first synthetically generated spectrum. So whatever we can do once, we can do twice, right? Our second spectrum. We made sure that the peaks are at a little bit different positions here. And now we are doing something fun. Yeah? We're actually saying that this S2 and this S1, they are, let's say, the spectra of two different components. So one is the, let's say, component A, and this is the component B. And we are mixing them by adding them together into a sample. And we are adding different concentrations of them, different proportions. Let's say we have the spectrum as one of this, we have the spectrum as two of this. And here we have been adding, I think, 20%, so 0.2 and 0.5 of this. Yeah, by the way, this doesn't need to, so percent is perhaps wrong. Yeah, this doesn't need to add up to 1. Yeah. So we have just some unit concentration here, where we add 20% of this unit concentration and 50% of this unit concentration. Yeah. And yeah, what is the spectrum doing? There is quite a nice properties, of course, also in some limits only. Yeah. But roughly, what the spectrum is doing, it is adding up. Yeah. So if you have this spectrum and this spectrum, you are getting the added spectrum here. Yeah. And this is kind of because you will now have both bonds, yeah, in the given concentrations that you inserted into them, and they are both creating these scattering effects that you will measure. Yeah? So it is additive here, the spectrum. Yeah? Then we coded a small mixing function that is actually doing this adding up here. And then we can mix that, right? Here we see the original spectra in red and blue, and the composed spectra is now black. It's just adding up. And now the big question, and this is now where people use Raman spectroscopy all the time, yeah, is like, you are not given the original spectra, and of course also not the information about their concentrations. You are just given the black composed spectrum, and the question is, what's the composition of this thing? Yeah. So let's say I make it a bit more simple. I tell you that there is an A inside and a B inside. So this information you have. I'm hiding this and I'm hiding this. And of course you have access to the spectra, right? And you only have this composed thing here. Oh. Yeah. Drawing business. So what would you do? Kind of. I mean, of course, we can guess in a cycle, yeah. But it turns out, like, of course, you could phrase that immediately, of course, to your favorite optimization problem, right? But there is a kind of more explicit solution to this simple case, right? We can actually formulate this as such a optimization problem in matrix algebra. So we can form a matrix S, then some concentration vector C, and then take here our measured spectrum, right? And the S is composed from the single spectra, and the C, this is the unknowns, right? This is our variables here, the concentration of this, and then we can minimize this. And in the perfect case, like if there is no numeric or measurement or whatever errors, that should be minimized to 0, right? It should have 0 residue. Of course, numerically measurement-wise, and so it will never have, but in principle, this zeroes out. Okay, then knowing this, we can actually rewrite this here. So fortunately, we don't have to solve this minimization problem, but there is a nice thing which in NumPy, which is from linear algebra, which is just LSD SQ function, which does that for us. And we run it. And that's the answer. It tells us 0.2, 0.5. And the residue is 10 to the minus 31. So, okay, it's 0. So worked very well. We solved the problem, right? And that's actually a really cool thing. I mean, yeah, I think that's a cool thing, yeah. Of course, what you can say now is, yes, but this was a kind of a very simplified case. Yeah? Okay, then I think now it's the time to get more complex. Yeah? So let's get to more involved spectra. So here we coded some more involved spectra. Actually, 4 of them. Yeah? They look like this, a bit more involved. In particular, they're kind of overlapping peaks now. It's starting to get a bit nasty. Yeah? And this is the composed spectra. So already, I mean, it doesn't look so nice already. So we run it, and it tells us here the coefficients. Here it tells us the coefficients, yeah. And we were even a bit tricking, because we were tricking insofar that we did not. Where is it? Yeah, here's the line I'm searching. We used 0.2 of this, 0.5 of this, and we didn't really put something from these 2 inside. Yeah. So this is kind of the case of you have a library of spectra, but you really don't know if they're inside the sample or not. You could imagine, of course, this goes on forever. Yeah, there could be 1,000 of these zeros. Yeah, where you have from glucose, from I don't know, like from all your chemicals or biochemical products, you have some spectra. Let's say. Yeah? And the nice thing is, it found it. And it tells us, I mean, it's not as nice as before, but 10 to the minus 5 and 10 to the minus 4 is kind of, yeah, I don't have that. Yeah, yeah. Wait, sorry, like where? Yes. For example, here you see this in principle, this cannot be the case, of course. It's because, and the reason is there is also, and this is a very good point, thanks to point this out, I think there is also a function from linear algebra that solves it only in the positive space. But good point, we should have taken that. I didn't, because it was just as formulated as a math problem, but good point. This already indicates something is here a bit fishy. Is this? But since it's not, I would say if it's minus 10 to the minus 1, I would be worried. But here I just consider this as 0. Yeah. But good point there. Yeah. Okay, let's get even more nasty. This is a composed spectrum with noise. Yeah. So we are assuming that all our spectra have noise, and the composed thing looks like this now, very noisy. Yeah. And we can do that again. Okay. Oh, I think these coefficients were actually for this. I think we had even nicer coefficients for the, yeah, it was even nicer coefficients here for the wizard noise. Yeah. So we were already showing the noise one. Yeah. But still, it can do that. Yeah. Okay, but now you can still say, okay, everything is still a bit synthetic, right? So can we do it with real spectra? Are we ready for real spectra? And let's try that. And this I find it a very, we had a very cool pointer from this Raman Spy package that was pointing us actually to in the tutorial, it's pointing us to a paper by Ho et al. From Nature Communications 29, and this is reporting some real bacterial spectra. It's a library of real bacterial spectra. And we can just load that here. Yeah, funnily, it's a Dropbox link, but we can load that. Yeah? Python can do everything. And this is the library. So here we see real spectra of bacteria. And for example, let's look at E. coli. Where is it? Here. There's 2 E. coli types. I mean, this is already, this is a complicated spectrum. Yeah? I mean, this is by far not as simple as, let's say, glucose or alcohol or something. Yeah? I mean, it's a super complex biochemical species, right? E. coli. So it will have a huge complex spectrum. Yeah? And this is what we see here, actually. Yeah? So this is how it looks if we zoom that out. So it has multiple measurements. This is why you see a little shadow. Yeah? But this is the mean spectrum we plotted here. And this is one particular, not mean, but really one spectrum. Yeah? So it looks really not too nice. Yeah? And we can take that, and we can take another bacterium. So let's take that one. Yeah. So of course, yeah, the spectrum looks a bit different, but yeah, also not too much. I mean, it's a lot of noise. And this is the mixed spectrum. I think now we can really not see by hand anymore what's inside here. Right? It gets very difficult. And now we can try our algorithm on this one. And funnily, it tells us very nicely the mixed coefficients. Yeah, so it's really very precise here also. I mean, the residue here is not too small anymore, so we have to be careful here. Starts to be a bit nastier. The algorithm is a bit at its limit, but perhaps we should do some pre-processing and use perhaps other algorithms for this. But still, it's doing its job very, very well. Yeah. There is one more complication. Yeah. And I think I will let you most of the time perhaps read that for information after the lecture. And the reason is, it's a super nice algorithm. I really love it. But it is perhaps not super practical for this purpose because when I showed you this spectrum, the so-called background signal has been already removed. So it is already something which has the baseline here at 0. This is not what you really get. What you really get is something like this. Yeah. So you get a kind of a background signal, and on top of this background signal, you get your spectrum here. And you have to have, of course, an algorithm that removes this background signal. And there is many nice algorithms around doing this. Yeah. So typically, you can really assume that taking your favorite Raman spy library or measurement equipment, it already removes the background signal for you. The only reason why I want to show you this is actually because I find this algorithm so beautiful. Or one of the algorithms. There's many algorithms to do this background removal. Yeah. But I want to show you this principle because perhaps you will use that at one day when you data process something. Yeah? And this is not specific to Raman. Yeah? This is in general something you have. This is specific to, you have a general trend, let's say here this, yeah? And on top you have some interesting stuff going on. And you want only the interesting stuff. Yeah? You want to remove this slow effect. Yeah? For example, this could be some temperature or time that you want to move away, or any kind of slowly moving your system around thing you want to remove from your signal. Yeah, would this be? So how can you do that? Do you have, like, you or someone online? Do you have an idea how you have a signal, and you want to kind of remove this slowly moving thing here? Like, do you have some idea how you would do that very intuitively without thinking long? Yeah, filter, yeah, completely. And what is one of the simplest filters you can do? Not completely, it's a filter, yeah. Yeah. You can derivate, yeah. Um, you could do that. The problem with derivating is very often that you're amplifying a lot the noise. Yeah? It's super sensitive to noise, and we already get super noisy data out of it. Yeah? So I would not do that here. But of course, mathematically, it would be something, yeah, to do. Yeah. So, but it's not too far. Yeah. So I will perhaps show you what I would do. Yeah. Like perhaps what you would, if you would need to code that. Yeah, what you would do is, like, you would say, um, I'm going kind of to remove the slow component. And what is the slow component? The slow component is kind of the average. Yeah. So you could have, for example, for this, let's say I'm sitting here. For a reason that you will see in a second. This is our, let's say, our x or time axis, whatever we want to put here. We are sitting here, and we are opening a window to the right and to the left, let's say, of 10 data items, and we are doing the average here. Yeah? And then we are subtracting the average from this signal. And we do this also here, and we do this also here, and so on. Yeah. So we are always removing from we have kind of a sliding window that is centered at the data point where we're interested in, yeah, for a certain reason. And then we're removing it. So the first thing is, why are we centering it around the data point? And I mean, we of course, you can only, for example, if this is time t, you could only do this after you have the data, right? The centering, or with a delay of 10. So, for example, people at stock markets, they often do this kind of averaging out the last 20 things and looking if your current value is above the average of the last 20 or something. Okay? But then you always get a little bit of bias from if you have a trend like this, right? And you are not centering, you are always using a bit this lower bias here. You're always a bit biased. So this is why it's better to center. And we have the time. I mean, we don't run our filter after during the Raman spectroscopy. We run it after, so we can completely center that. But perhaps the interesting thing why this intuition of taking the average works is, what you're kind of doing to the average is, let's say you have a signal here. So this is our signal, and this is my window, right? So this is, let's say, I'm interested in this. This is 10, 10. When I average, I kind of do something very interesting. I'm kind of fitting a constant polynomial in a least square way. That's the average doing. Huh? So let's say these are my data points. That should be 10. I'm not doing 10 here, but you get the point. And I want to find the constant function, let's say here, that has the minimum squared error. So the squared error would be here, 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 and here. And I'm squaring everything and summing it up. Yeah? And I want to minimize this. Yeah? And let's say the minimum is actually this line here. So, yeah, probably not, but it's like that's something. Yeah, you get the point. Yeah, and of course you could run an optimization problem to find this. We could formulate this as an optimization and do it with gradient descent or whatever, like your favorite machine learning algorithm. You can find this constant function C that minimizes this sum of squares. Yeah, but actually you can analytically solve that, and the analytic formulation is actually the average. The average of these y values gives you actually the C value that minimizes this. And that's super neat because averaging is, I mean, it's super fast and it gives you this. And this is kind of, this, if you remove now this C, this kind of gives you the background signal in this small localized area. Yeah? Now you can say, well, I'm not so happy with actually fitting a order 0 polynomial, right? This is an order 0 polynomial, a constant function. I'm expecting much more something like a line, yeah, because my general data, my general background will look like this. I don't know, and then my signal is on top of this. Let's say, yeah? Okay, but nothing prevents you from not fitting a line, not fitting a constant, but fitting a line inside. Now you can ask for the line with the minimum squared error, yeah. And actually, again, this can be solved analytically. You don't need to you don't need to solve this and then you can ask, okay, actually, I'm expecting such a function, right? So I'm going to fit the least square. I'm going to fit the least square second order polynomial inside it. And this is my background. So this would be for backgrounds that look like this, and so on and so on. You can go crazy. You can go to put the seventh order polynomial inside it. And this is a very, very nice concept. Yeah? And these filters have a name. And they're called here Savitsky-Golay filters. You might have heard that. And yeah, we linked you the paper and the Wikipedia article here to read about that. Just help me check the time. Oh, sorry, I'm already 5 minutes over. Very sorry about that. I'm just perhaps, and we're actually at the end. Yeah, I mean, this is just running this. You don't have to implement this filter. You can just load it from this SciPy signal library. You can run it, and you can get the background. This is the real background, and what the filter finds as the background. Looks very nice. And this is the real signal, and the background established signal. So looks pretty nice. And that's the end. We have here some further literature. There are very nice papers that you might check out if you want to know more about the different methods. And that is it. Any questions for this? Yeah. If not, I think we can stop here. We have seen what we have seen. We have seen absorbance, we have seen optical density, and then we went to Raman. But keep in mind that all these principles, they are not specific to these methods. Yeah, you could very well, for example, look at, I don't know, near infrared spectroscopy, and you would get spectra very similar to this or other spectra. So you can even compose your very customized spectra from discrete spectral data that you invented, and there's no problem. Yeah, it has to fulfill some certain properties of linearity and so on, and then you can run all these algorithms. Okay, and thanks a lot. and until next time. Yeah? So.